And we march on through a study of integration techniques, again looking at, hey, here's this integrand, I'm not quite sure what to do with it, what do I do with it? And today we look under the banner of trig substitution. And you're going to take a look at example 1 and you're going to say, trig substitution? Really? I need trig to do that? And the answer is yes. Consider the following. This thing right here looks like it's a side of a right triangle. It looks like there's a perfect square, there's a perfect square, there's a square root. This lives on a right triangle somewhere. And because it lives on a right triangle somewhere, trig is probably involved. And in fact, all of our integrands today are going to involve differences of squares or sums of squares in some capacity. And I have a nice, easy 4-step process that helps us get through exactly what we're looking for. Step 1 will be to build a right triangle. And the right triangle in question is pretty straightforward. We have this side of unknown length, right? Now, how did it get to be that way? It got to be that way because the differences of the squares there, well, that tells us what the other two sides are. The hypotenuse is the square root of that, and the other leg is the square root of that. It really doesn't matter who's on what leg, because this is going to show us there's your hypotenuse, there's your other leg. Doesn't matter where these sit. Where these sit determine what trig functions we use. We're going to name a theta. I like to put my theta opposite x for reasons that should be clear later. Step 2. Step 2 is to sub for every expression involving x. And that's easy to do. That's easy to do because we're going to establish two relationships here. We're going to establish a relationship between the linear term and the constant term. And we're going to establish a relationship between the radical and the constant term. On the right triangles in these trig sub problems, there will always be a linear term, there will always be a constant term, and there will always be some radical. And if you can determine the relationship between the linear term and the constant, and between the radical term and the constant, you're okay. Now, in terms of this angle theta, x over 1 is the sine of theta. And the radical over 1 is the cosine of theta. So when we go to our integral is the integral of the radical, and the radical is cosine theta. Now, what's dx? Well, I know that x is sine theta, so dx is cosine theta d theta. Cosine theta d theta. You know what? We did this yesterday. We did this. We talked about how to do this, and that's step 3. Step 3 is to evaluate the integral. And I remember we talked about how to do this. This is a case 3 from our last lesson. And we learned that cosine squared theta is 1 plus cosine theta over 2. That's what we learned. That's what we learned. And so we know how to do this. This is theta plus sine theta. Nope, that's not true. That's not true. And to show you what a nice guy I am, I'm not even going to go back and redo this. It's 1 plus the cosine of the double angle. And And all of you who were screaming at your YouTube, you were right. It's 1 plus the cosine of the double angle, which means, and I'll pull out the eraser for this, which means that we have theta plus 1/2 sine 2 theta over 2 plus a constant. And that's not very neat. So let's make it a little bit neater. Theta over 2 plus 1/4 sine 2 theta plus a constant. Now, you can guess where we have to go from here. It's not terribly difficult to figure out that we're not going to leave this thing in terms of theta. We are going to substitute back. So neither of those is very enticing. Theta. What is theta? Well, theta is this thing right here. If I want theta by itself, I've got to move sine to the other side, and the way we do that is with the inverse sine function. I mean, if we think about it, theta is the angle whose sine is x. And since theta is the angle whose sine is x, that is our substitution. And then sine 2 theta. Well, you may remember from your Triggy work that that's 2 sine theta cosine theta. That's a really nice thing to have handy because 1/4 times 2, I can do that. And then sine theta, that's easy. Cosine theta, that's easy. And we're done. Oh, this is ugly, don't get me wrong, but we're done. And we're done in 4 fairly straightforward steps. We build a right triangle, use trig to substitute out all of the xy stuff, evaluate the integral using our trigonometry tricks, and then substitute back. Trig is literally a middleman that we use and then chuck to the side. I will illustrate twice more. Integral of 1 over x squared times the square root of x squared minus 9 dx. And again, it's got perfect squares, difference of perfect squares, in a radical. There's some other stuff here, but that's okay. This is the signal, square root of a difference of perfect squares, that trig substitution is going to work really fine. Step 1 was build a right triangle. So when we're building the right triangle, the hypotenuse is x. The other side will be the square root of this. And then you have some radical for some reason hanging out over here. And you can check yourself with the Pythagorean theorem. This works just fine. The bigger of the two, that's the one on the left. That tells you what the hypotenuse is. The other one is one of the legs. I like the radical here. You don't need to have the radical there. In fact, we could switch them if we like. Step 2. Step 2 is to do a sub out where all of the xy stuff gets replaced by theta e stuff. And if you remember, the way we do this is we find a relationship between the linear term and the constant term, and then a relationship between the radical and the constant term. Well, the linear term is to the constant as secant theta, and the radical is to the constant term as tan theta. So when I take a look at what we've got here, x squared, well, x is 3 secant theta. And the radical, right? So what's dx? Well, if x is 3 times the secant of theta, then dx is the derivative on that times d theta. Well, why is that advantageous? That's great. That is great. Because when we get to step 3, evaluate the integral, and we find out that this is 1/9 comes out from the semi-permeable membrane, secant theta in a denominator is cosine theta up top, I can do this. I know the antiderivative of cosine theta. Oh, that cleaned up very, very nicely. That cleaned up very, very nicely. So now all I need is sine theta. Step 4 says we go back and back substitute. Well, what's sine theta? Sine theta is opposite over hypotenuse. Done. Oh, isn't that clever? See, this is a much easier integral to do than this one is. It's murder to get there because we have to use trig, but this integral is much easier to do. Well, I'll go one more with you. Integral of x squared over 1 plus x squared. And here you're thinking, there's no radical. I know there's no radical, but there is a sum of perfect squares. And so I'm still going to try to build a right triangle. And it's a sum of perfect squares, so this talks about the hypotenuse. It talks about the hypotenuse. That's a sum. The sum has to be the biggest side. And so it belongs on the hypotenuse. The other two sides are x and 1 in some order. It really doesn't matter where. So step 2 says to sub out all the xy stuff in favor of triggy stuff. And if you remember, we do that by establishing a relationship between the linear term and the constant term, and between the radical expression and the constant term. Mm-hmm. Mm-hmm. So we make a substitution. X squared. 1 plus x squared. That's the square of this radical. Dx. Well, if x is tan theta, the derivative on x is the derivative on that, d theta. What's the advantage of that? So we go to step 3. Step 3 is to evaluate the integral. How did we do the integral of tan squared theta last time? Well, we wrote it as the integral of secant squared theta minus 1. We used a trig identity to get us something whose antiderivative was obvious. Tan theta minus theta plus a constant. And so now all we have to do is sub out all the triggy stuff for xy stuff. Tan theta, we know what tan theta is. Theta's this guy. Theta is the angle whose tangent is x. Isn't that nifty? Isn't that nifty? Build a right triangle. Establish relationships between the linear term and the constant term, between the radical and the constant term. Make your substitutions, remembering to take derivative here to do it. Evaluate the integral, sub back. Every problem goes the same. Every problem goes the same. Couple of things for you to consider as you're trying to figure out if you know what you're doing or not. Let's do the integral of 1 over x squared times radical x squared plus 4 dx. And let's do the integral of x squared over radical 9 minus x squared dx. This one's pretty straightforward. This one's a little bit tougher, looks a little bit uglier at the end. Okay, so that's 15 minutes of video watching, but it'll probably take another 10 or 15 minutes to cement this down. So I hope you have the time to do that before you get to class, and I'll look forward to seeing you then.